This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Welcome to Lecture 6, everyone. All right. So just another reminder that your tutorials, your F4 labs, and MATLAB workshops starts next week. Okay. So please do go to your allocated tutorial and workshop and F4 lab sessions. Now, do you all know where the F4 labs are? No. Walter Bassett Aerodynamics Laboratory. All right. Now, I'm sure some of you are going to email me during the weekend and ask me where is it. So a couple of students a couple of years ago made these slides for you guys, right? How to get to the Walter Bassett lab. So you all know where this is, roughly. You can see the House of Cut coffee shop in the background, right? So you are at location X there, right? Here. Okay, so you want to walk along this alleyway, okay? All right. And there's a turning to the right. Okay, so as you're walking there, there's a junction to turn to the right, okay, which looks something like this. So turn right there, okay. Go along this alleyway, right? Walk straight to the end, and you'll see this building. You all should know this building. This is the mechanical engineering building, right? Okay. So go through these doors, right? On the left, as you go into the building, you'll see the male toilets. Don't stop. Just keep going straight. Okay. You want to go to the female toilets, all right? Not to the female toilets, but towards the female toilets. All right. So you can see this door on the left here, right? It also says the Walter Bassett Aerodynamics Laboratory. Okay, and that's where you want to go to. So you have to walk up 2 flights of stairs. Okay. And you'll see this very dangerous-looking door, right, with a lot of warning signs and lasers and caution and all that stuff. So what you want to do is you want to press the doorbell, okay? And someone will open the door for you, okay? Right, because this is a lab, always remember you want to wear closed shoes, okay? No sandals, no tongs, right? Please wear closed shoes and appropriate clothing as well, okay? As when you conduct the lab. So if you do not wear proper clothing, the demonstrator has the right to ask you to attend another session. Okay? So please dress appropriately. Okay, one more announcement. Do you all get any notifications when I upload stuff on LMS? Yep. All right. So some of you would know that I have uploaded the potential flow assignment on LMS. So please have a read at your assignment, okay, especially before you go to your MATLAB workshops next week, okay, so that you roughly know what you want to get out from those workshops. So this is the front page of your assignment, okay, and the assignment is due on the 13th of September, so roughly, I think about five weeks, okay. So Friday the 13th, it's a very unlucky day, okay? But it's only unlucky for you if you do not submit it before the 12th, before midnight of Friday the 13th, okay? So please submit it before then. If you try and submit it after that, because it's an online submission, it automatically closes, okay? So the assignment has to be done in groups of 2. Okay, and both you and your group mate will get the same mark. Okay, And if you choose to do this assignment alone, there will be no concession given to you, right? So, therefore, please choose your group partner carefully, right? And this is submitted via LMS, right? So you only need to submit one assignment per group. You will be using some programming language to do your assignment, so you can use MATLAB or C. I do recommend MATLAB, as it's a bit easier to plot the graphs. Okay, and there's a few things which are not allowed to use in MATLAB, a few functions which you shouldn't use, such as streamlines, OD, XX, and you shouldn't also use contour to visualize your streamlines, okay, or phi. So you want to generate your own code to plot your streamlines, which we will be talking more about in the workshops next week, MATLAB workshops. Okay. So in the previous lecture, I showed you this MATLAB script which I did. Well, not I, but Nick, right? And basically, we know our stream function. We can then find out our velocities u and v. And once we know our velocity vectors, we can seed particles and watch it move, right? And these particles which are moving are our streamlines, as the path lines are equal to streamlines for a steady flow. Okay? Right, and we saw for this particular case that the smoke particles hits the bystander and the bystander dies. All right? So for your assignment, you would have to do something similar, right? You have to generate a MATLAB code which would allow you to trace these particles, right? To track these particles. So what I showed you for my code was a very simple Euler time-stepping scheme, which is first order accurate, but you are expected to use RK4 in your assignment, which is fourth order accurate. Okay, and again, that will be elaborated more in your MATLAB workshops. Now, there was one very glaring problem with our first attempt of the smoker's problem, and that is our bottom boundaries, right? So you can see that there's flow coming in and out from our floor, but that's not physically possible, okay? So we want to make sure that our bottom boundary here is impermeable, right? So basically, my velocity v is 0 along this line here. And to do that, I then introduced the method of images. Okay, so basically creating a mirror image of all the floor features behind or beneath the required boundary, right? And this is to ensure that our boundary becomes a streamline. And we know that for a streamline, there is no velocity perpendicular to it. So no flow can cross through a streamline. Right, so we then had a second attempt at this smoker's problem. And this time we have added our images for our source and also sink. Okay. So both of them has the same strength as the actual source and sink, but they're just located in the opposite direction. Okay. Right, so we can then have an expression for our stream function for this flow. Okay, and you have streamlines that look something like this. Now, initially I posed this question where how far the bystander has to be so that it does not get the secondhand smoke from smokers. Well, another way I could pose this question is how strong does your exhaust fan has to be relative to the source or to the smokers, all right, so that the bystander does not get smoked. Right? So basically, what is the ratio for QE over QS I should have so that our bystander does not get smoked? Okay, and if I increase this ratio here, so basically making the sink stronger while maintaining the source, right? You can see that my streamline patterns are changing. Okay, and it affects the stagnation points along my x-axis. As you can see, it's becoming smaller and smaller, and I can then find the optimum QE over QS ratio, which will ensure that the bystander does not get smoked. Okay, everyone follow so far? Yep. So in the previous lecture, we derived our stream function. We also had an expression for our velocity u and also v. Okay. Oops. And what we did next was to consider the stagnation points along the x-axis, right? And we got this expression here. So our stagnation points along the x-axis depends on QE over QS, right? Where QE over QS ranges from greater to 1 to less than LE squared over LS squared. Right? Okay, so you all understood this, how I got this here? Yep. Okay, good. So that's the stagnation points along the x-axis. Now, we are going to look at stagnation points along the y-axis now. Okay, so when x equals to 0. So let's have a look at our velocities. So when x equals to 0, can anybody tell me what's my u? Right, u is going to be equal to 0. Okay, very good. And for v, I'm going to get v equals to qs divided by 2 pi times 2y divided by y minus ls times y plus ls minus qe over 2 pi 2y y plus le y minus le. Okay, and basically these two all cancels out as well. Okay, so stagnation point occurs when u and v is equal to 0, right? Your u and v velocities are equal to 0. And from our v, for our equation for v, you can see that our stagnation point occurs when 0 equals to qs over pi y squared minus ls squared minus qe over pi y squared minus le squared. Okay, everyone's following so far? Yep. Now, what's one possible stagnation point? Y equals to 0. Okay, very good. So ys equals to 0 is a stagnation point. Okay, so that's one possible solution, right? And I've just used subscript S for stagnation point. Okay, but there is also another, well, two more possible locations. So all I'm going to do is I'm just going to rearrange my equation a little bit. Sorry, this term cancels out as well, right? So I'm going to get Q S over QE YS squared minus LE squared equals to YS squared minus LS squared. Okay, and I'm just going to bring YS to the left-hand side so I can have an expression for YS in terms of QS, QE, LS, and LE. So I should get QS equals to plus minus square root QS over QE L E squared minus LS squared QS over QE minus 1. Okay, so all I've done is I've rearranged YS squared to the left-hand side, and then I take the square root of the whole thing. Right? So, when are we going to have stagnation points along the y-axis? So when QS over QE is so in order to have a stagnation point along YS, this has to be a positive value, right? Okay, and that's possible when QS over QE is greater or less than 1? Greater, right? So when QS over QE is greater than 1. We have real solutions. And also when, okay, so when QS over QE is greater than 1, we know that this term here is greater than this term here, so it's positive, right? And the denominator is positive as well, so we get square root of a real, or of a positive value. Now another alternative is when this term here is negative and this term here is also negative. Okay? So this also occurs when QS over QE is less than LS squared over LE squared. Okay, so we have real solutions when QS over QE is very, very large, or greater than 1, and when QS over QE is very, very small, or smaller than this value there. Okay, everyone clear so far? Yep, so I want to ask you, right, if let's say there is no real solutions for YS, where do you think are our stagnation points? Exactly, right? So if we do not have stagnation points along the y-axis, all right, if it's a square root of a negative value, it means that basically our stagnation points are along the x-axis, xs, okay? So, oops. So let's have a look. Oops. Okay, so this is for... Alright, so this is our stagnation points along the x-axis, alright? So when QE over QS is greater than 1, okay, we have a stagnation point along our x-axis. Okay, and we have a stagnation point along the y-axis when QS over QE is greater than 1. Okay? Right, which looks something like this. So now your stagnation points is at the top here, and another one is below in the below the imaginary plane, right? Okay, so in this case here, the source is much greater than the exhaust, and you can see that all the smoke particles is going everywhere, right? And only some of them are trapped by the exhaust fan. Okay. Now, the other solution is when the source, right, is much smaller than the sink, right? And now your stagnation points are here and below in imaginary as well, right? So you can see that in this case, your exhaust or your sink is very strong, right? And immediately whatever smoke which is emitted by this source here gets trapped inside, and it's pulling out all the ambient air inside as well, okay, into the sink. Right, so now we know how to solve this smoker's problem, right? And in the future, when you're an engineer, okay, this is a potential job for you, right? And all you have to do is you can just reply your client and tell them that, so if I do not want the bystander to get smoke, all I have to do is change this parameter QE over QS, which is the strength of the exhaust to the strength of the sink or the smoker, all right? And hopefully you should be able to tell your client that if QE over QS is greater than 1, then the non-smoker should stand X meters away from the smokers if he or she does not want to get secondhand smoke. Right, but if QE over QS is less than 1, all right, or if your exhaust fan which you have installed is not strong enough, it's quite weak, then everyone will get the smell of smoke. Okay, and then you can then charge a ridiculous $200 per hour and get $1,000 in your pocket for a couple hours of work. Okay. Right, so everyone's good. Everyone understands the smoker's problem. It's quite a popular question, I would say. Okay. So I'm going to show you some variations of the smoker's problem. So one very common mistake is that you forget your negative when you're calculating the velocity, the v velocity. Okay, so please don't forget to include your v velocity. Okay, so if you forget to put a negative here in front of your del psi del x, okay, you'll get a streamline that looks like this. Okay, and you would very happily tell your client that no one's going to get the secondhand smoke because it's all going to get sucked by the exhaust. When in actual fact, your streamlines are going to look something like this. Okay, and someone dies and then you get sued by your company or something. Okay, so you don't want that to happen. So please be careful with the negatives, all right, in your vertical velocity v. Now, what happens if I put a uniform crosswind to this flow? Okay, so let's say I have some flow from right to left. Okay, and I can do this, right? Because I know that my uniform flow satisfies continuity. It satisfies my momentum equations, right? The Laplacian of psi is equal to 0 for a uniform flow. So I can just sum it into my stream function. And what I'll get is, I'll get something, the streamlines would change, the streamlines patterns would change quite a bit. Okay? And now you can see that the region where it's filled of smoke, right? This region here changes as I increase my free stream velocity. Right? Okay. One variation of this question, okay, is that we can ask you, what if instead of having just one exhaust fan, we have two separate exhaust fans with half the strength? Will that be more efficient? Right? So that's another question which we could potentially ask as well. Okay. And again, when you have these differences, your streamlines are going to change as well. Okay. So just out of curiosity, if let's say you have a source and two sinks, how many images should you have? Oh, I was showing it in my... Yeah, 3. All right? You should have 2 sinks and a source image. Right? So you should have, all in all, you should have 6 terms in your stream function. Okay? Right. So now we're going to look at a different type of flow now. So let's say we have a source and a uniform flow. So a stream function for a source, you already know what's that, right? That's just Qs over 2 pi arctan y over x. Okay. And now if I add a horizontal uniform flow, okay, and my flow is from right to left, okay, therefore my stream function for that uniform flow is going to be negative u infinity y. Okay, negative u infinity because I'm going to the left-hand side, right? And you can see that as I increase my free stream velocity, the streamlines coming out from the source are going to change, right? Okay, and basically what I'm doing is I'm just increasing the ratio between u infinity and Qs. Okay. Right, so if I look at the streamlines of the uniform flow, you can see that the streamlines of the uniform flow are also affected by the source, right? And you can see that the uniform flow goes around it. Okay, and again, I'm just increasing the ratio u infinity over Qs. Okay, and this looks, well, not really an airfoil, right? But it looks quite similar to an airfoil, right? Which is our ultimate goal. We want to simulate we want to model a flow over an airfoil, right? So this is another attempt at that. Okay, so the stream function for this flow is negative u infinity y plus Qs over 2 pi arctan y over x. And the next thing we would like to do is we want to find the location of the stagnation points, and we want to also draw the separatrix line. So remember, the separatrix line is just basically your streamlines which crosses through your stagnation points. Okay. So would you like to do this together, this question? Yes? Yep? No? Yes. Okay. All right, so let's try and do it together. Right, so this is my flow field, my streamlines. In this case, I already know what the streamlines kind of look like, but in the exam, you do not know what the streamlines look like, and you actually have to sketch this out, right? So the first step is always to, well, typically, is to write down your stream function. So I'm going to have psi equals to negative u infinity y plus qs over 2 pi arctan of y over x. Okay, and my first term is just a uniform flow. Okay, from right to left. Okay, and my second term is just a source term. Okay, if I want to plot the streamlines, what information do I need to know? What's the next step? What information can you get from your stream function? U and V. Okay, correct. So normally the next step then is to find your velocities, U and V. Okay, so that's another step for you to find your stagnation points and then your separatrix. Okay, so U is just equals to del psi over del y. Okay, so my first term just becomes negative u infinity plus, and I hope all of you know how to differentiate arctangent now. So it's just going to be qs over 2 pi x over x squared plus y squared. Okay, I'm going to call this equation 1. And similarly, I can find my velocity v as well. Okay, and velocity v is just v equals to negative del psi over del x. Okay, so if I differentiate this with respect to x, this is going to be equal to 0. Very good. And I left with just velocity due to my source, which is qs over 2 pi y x squared plus y squared. Okay, so we have our velocities now. So the next step is to find our stagnation point, and our stagnation point means our velocities u and v are 0. Okay, so velocities u and v are 0. So hopefully from the equation you can see that when y equals to 0, what's v going to be? 0. Very good. Okay? So if you go back, right, so when y equals to 0, v has to be equal to 0. Oops. Okay, so for u, okay, the stagnation point is going to occur when 0 equals to negative u infinity plus qs divided by 2 pi xs. Okay, so very easily all I have to do is just rearrange this and I can find an expression for x. So, sorry, xs. Right, so therefore xs is equals to qs over 2 pi u infinity. Right? So my stagnation point depends on Qs and u infinity. Okay, so I'm just going to write it down. Therefore, stagnation point occurs at Qs divided by 2 pi u infinity and 0. Okay, so that's my coordinates of the stagnation point. Everyone okay so far? Yes? Okay. So now I got my stagnation point. I want to find my separatrix. Right? You want to find an equation for a separatrix. Okay, so we want to find equation for a separatrix. Okay, so can anybody tell me how can I find the equation for a separatrix or equation for a streamline? Any guess? So we know our stagnation point. We know that lines of constant psi are our streamlines. So how are we going to get the streamline which crosses through a stagnation point? Correct. Right? So all we have to do is sub our stagnation points into psi. Very good. Okay, and I'll get psi equals to negative u infinity 0 plus qs over 2 pi up 10 0 over qs over 2 pi u infinity. Okay, so this term here is 0. What term is this? What does this term equal to? 0. Okay, so therefore psi equals to 0. Right, so the constant value for a separatrix is 0, right? The psi value is 0 for a separatrix. Okay, and all I'm going to do now is just substitute it back to my stream function. Okay. Any questions before I move on? No? Everyone's okay? Okay, so I'm going to substitute back psi equals to 0 to my stream function, and you'll get 0 equals to negative u infinity y plus qs over 2 pi up 10 of y over x. Okay, and I can just rearrange it so I find an expression for x. So x is just going to be equal to y tan 2 pi u infinity y over qs. Okay? Right, so all I've done is I've taken u infinity y to the left hand side here, okay, and take these terms over as well and rearrange it so that x is some function of y, u infinity, and qs. Right, so this is our equation of a separatrix. Okay. Some of you also might also know that another separatrix occurs when y equals to 0, right? Okay, so you all should know that another potential solution is when y equals to 0, and that's just because when I substitute y equals to 0, it also satisfies equation here. Right? Okay, so we have this equation of a separatrix, and we want to make use of this equation to try and sketch this flow. Right? So you want to gather as much information as we can from this equation so that we can sketch this uniform and a source flow. Okay, so I'm going to consider a few cases. The first one is when x approaches infinity. Right? I want to see how my what values do my separatrix approach. Okay, the y values of the separatrix, I mean, right? What values does it approach? So when x equals to, or when x goes to infinity, so the tangent of 2 pi u infinity y divided by qs, what must that approach? Oops. Okay, so we want this when x approaches negative infinity. Oops. Negative infinity. So this term here has to approach 0, right? Yep. So that term there has to approach 0. Sorry, it's negative infinity, by the way, not infinity. Okay. Right, so therefore, tangent, the term inside there has to be equal to be pi. Okay, because we know that tangent pi equals or approaches 0, right? So all I'm going to do is try and find an expression for y. Okay, so if I rearrange this, I'm going to get y equals to plus minus qs over 2u infinity. Okay, everyone agree? Right, so I'm going to speed up a little bit. So I'm going to consider the case when when x approaches 0. So now tangent 2 pi u infinity y divided by qs. Okay, that has to approach infinity now. Okay, it has to approach infinity so that the denominator, so that the whole thing, the denominator has to approach infinity so that x goes to 0. So I'm going to get 2 pi u infinity y divided by qs. Okay, this has to be equal to pi over 2. All right, and we know that tangent of pi over 2 gives us infinity. All right. So therefore, y is going to be equal to plus minus qs over 4u infinity. Okay, so from this information which we have gathered, okay, we can then kind of sketch our streamlines. Right, so going back here, now we know where our stagnation points are, right? Okay, so we know the stagnation point is at somewhere around here. Is that right? Yep, and the coordinates are, what's the coordinates? QS, yep. Okay, good. QS over 2 pi u infinity. Right, and y equals to 0. Okay, and you know that, our separatrix, there's two lines, right? One, the easy solution, it just goes along the x-axis. Right, so I've drawn it in red. I don't know whether you all can see it. Okay, and the other separatrix that we have goes somewhere along here, right? Okay, and that's just the equation that we got here, which is the, which is this equation here, right? Okay, so I'm going to draw this a bit nicer, I guess. Okay, so I'm going to draw the other separatrix line. Ah, shucks. Oops. Okay, yep. So it should look something like that. Now, remember stagnation points are saddle points, right? So, hopefully you know that if I have a flow coming into my stagnation point, right, and another streamline where the flow is going into my stagnation point, then these two here have to be going in or out from my stagnation point. Out, right? It has to go flow out from my stagnation point. Okay. Right. Now, there's a few more things which we know. We also know the location of when x equals to 0, right? Okay, so you should also label these points when you sketch your stagnation point. So that's basically x equals to 0 plus minus qs divided by 4u infinity. Right? And we also know that this separatrix, the height of this separatrix, okay, we know that that as x approaches negative infinity, our y value is plus minus qs over 2u infinity. Okay? And you should also not only draw the streamlines, but you should also draw the arrows, right, pointing the direction of the streamlines. Okay, so the flow is going towards the left here. Right, so for this question, we kind of cheated because there's already some streamlines which I've drawn. Okay, but in the exam, typically I would give you some simple flows, right? And then you're asked to find the velocities for that simple flow. All right, find the stagnation point, and also find the equation for the separatrix, and finally sketch the streamlines for this flow. Right, so that's a typical question that you might get in the exam. Right, I think I should end it. I should end here, and we'll continue on Monday next week. Right, thanks.
For the x approach to negative infinity.
Yep.
Yeah. Actually, we know the tan function is a periodical function.
Yes.
Why?
So you can get pi or 0, right?
And k pi is also a 0.
Yeah, that's true. But
So why we pick up
so
pi?
when x goes to negative infinity, right? So basically it means that it's going towards the left here,
Yeah.
right? So tan has to be positive pi or negative pi.
Yeah.
It can't be 0 because 0 is going to infinity. So that's approaching positive infinity, not negative infinity.
But what if we pick up 2 pi?
Well, 2 pi, well,
Yeah. But at first, I assume it should be 2 pi and
oh. No, but 2 pi is 0, right? 2 pi is 0. So 2 pi is here. But then this approaches positive infinity, not negative infinity.
so we have to use the negative infinity.
Yes, because we are looking at negative infinity, right? For the streamlines here.
And for the x equals to for the x approaching to 0, we also use pi on 2 because we can use pi on 2 plus k pi is also, for Okay, then like
Yeah,
pi on.
we take the simplest angle, I think. Yeah, so we take the simplest angle. So it can